Okay, so good afternoon, everyone. So today I will present an application on a topic a little different than the one that are usually considered here. And so I should start talking about precipitation. So the measure of precipitation is actually very important for our society, since it has an impact on quite a wide range of fields. And the measure of precipitation is obtained by means of precipitation gauges, of course. And those can be divided into major categories. So the first one is catching type gauges that use a funnel to collect incoming hydrometers, so be it rainfall or snowfall. And they are relatively low cost since they use very simple functioning principle. They are therefore also easy to maintain, and this made them widely adopted by national weather services. However, they only provide the precipitation intensity. Instead, the other kind of gauges are the non-catching type ones. Those are a new kind of gauges that rapidly gain in momentum, and those do not have a funnel. Instead, they measure each drop often contactlessly, and they have a much higher cost since they use a very complex measuring principle like a laser beam, radar, or imaging system. However, they require very little maintenance, and they also provide the particle size velocity distribution during precipitation event. And this made them quite useful for research application and are being adopted by national weather services. And so here below, I left you some example of these kind of gauges. And so, as all kind of gauges, those can be affected by some kind of bias. And so for precipitation gauges, the first kind of bias is instrumental, and it is due to the measuring principle that the gauge used or its construction. However, they can be reduced or mitigated by the calibration. The other is instead environmental bias, and this is due to the environmental conditions that are present at the gauge body when it's measuring. And those can be mitigated by means of correction curves. Considering the latter, the wind is the primary source of environmental error in precipitation gauges. And this is due to the gauge body itself that when immersed in a wind field, it behaves like a bluff body object and create a strong velocity gradient. And those can divert incoming hydrometers and therefore reduce the number that are actually sensible. And this problem is actually known by more than 150 years. And some hardware solutions are available, but usually, like the one in the picture, usually are feasible only for test sites and not for a typical installation. And so the evaluation of this kind of bias is a necessity. And several approaches are possible, like a field intercomparison, wind tunnel experiment, or in this work, a numerical simulation. And so, first of all, we can talk about the gauge that were investigated during this work. The first is the EML calyx, that is a tipping back catching gauge that is used to measure rainfall intensity. And this gauge will measure the time intervals between the consecutive tips of the reservoir where the precipitation is collected. And this gauge is of interest since its shape was specifically designed to minimize the impact of wind. The other gauge investigated is a new kind of gauge. It's part of the non-catching type family, and it is an optical gauge that uses a laser beam to measure both diameter and fall velocity of hydrometers that cross its sensing area. And for both gauges, the main responsible for the wind-induced bias is the separation layer that is produced above the collector for the EML calyx or the sensing area for the T-slab precipitation. And for the first kind of gauges, the catching one, some correction are available, while for the newer ones, the non-catching gauges, and no correction are available, even if, for example, for the T-slab precipitation monitor, literature examples are present of this kind of bias. And so the evaluation of the wind-induced bias requires several steps. And so using computational fluid dynamics, we can evaluate the wind velocity field of the gauge immersed in a wind field. Then, using Lagrangian particle tracking, trajectories of incoming hydrometers can be computed, and by the analysis of those trajectories, correction curves are obtained. So in this test, in this work, I'm focusing on the evaluation of the velocity field around the complex geometry of this kind of gauges. And I tested two different numerical approaches that I also validated here. So the first one is using a Eurance simulation with a k-omega SST turbulence model and a local time stepping approach to reduce the computational cost and still provide a stable steady state condition. The other method is instead largely simulation, much more costlier, using the wall adaptive local eddy turbulence model and full second order scheme and very low CF number. Okay. And here some first results for the EML calyx. So for the EML calyx, two different turbulence condition, base flow turbulent condition were tested. Since these usually we are considering low turbulence, but in this case, since this gauge our position is close to the ground, we can actually have a very high level of turbulence in the base flow. And so two cases were tested. The first is a simple mesh with 1.2 million cell, while in the other, a turbulence grid was inserted inside the domain, increasing the cell count to about 0.7. In both cases, a mesh construction was obtained using the NAPX mesh utility, and you can see them. Okay, here I use standard quality parameters. And so the first results comparing the two turbulence condition is that quite a difference is visible in the separation layer that is formed above the collector. And so for the high turbulence, we see both lower gradient, lower maximum values, lower downdraft and updraft. And this is actually expected since the higher turbulence tend to reduce gradients. However, can have a significant impact on incoming hydrometer trajectory since they experience lower values of velocity. Then the other instrument tested is the laser precipitation monitor, and this gauge instead has a very complex non-radially symmetric shape. And so here 9 different meshes were constructed considering 9 different wind directions. And so since a large number of mesh were required, both the gauge body and the refinement volumes around it were constructed using a CAD software, and then scripts were used to run both block mesh and SnapX mesh to automate mesh generation. Mesh resolution in this case was evaluated computing the ratio between the integral length scale and the grid length scale, and I'll show you some example in the next slides. And I also try to improve mesh quality parameter in respect to the previous case. And so here is an example for in the left for the Urans meshes with, that were from 0 to 180 degrees and were composed of about 4 to 5 million cells, while for less simulation, only due to the cost, only 2 wind directions were considered, and meshes between 20 and 25 million cells were produced. So we can start with some Urans results. So here 9 wind direction and 5 wind speeds were computed, and starting from the RL parameter, we see that it is above 5, that is a reasonable value in most of the domain, except very close to the gauge body. In the moving image, we see a quite different pattern that develop around the instrument sensing area depending on the direction. And so it's clearly visible that maximum disturbance near the gauge sensing area is when wind direction is parallel to the laser beam, while minimum disturbance is had for wind direction perpendicular to it. This is also clearly visible using showing the criterion image that I presented here. So for the upper image, for wind direction parallel to the laser beam, quite a strong turbulent structure are present directly in the path of the laser beam, while in the second image, no visible disturbance is present. Then we can see instead larger dissimulation results. And so here, only 2 wind direction and 2 wind speeds were simulated. And of course, for this case, a large cluster was used. Here, the RL parameter is above 10, that is base values for less in most of the domain. However, it's still not perfect above the instrument sensing area. Also, in this case, criterion show very strong turbulence generation, and results were considered in this case both in terms of average field, that is quite similar to the one provided by the Euro simulation, and instantaneous flow velocity. Other than flow velocity is also useful to observe turbulence kinetic energy. These are from the Euro simulation. And so, as we already said, in the case of the two leftmost and rightmost blocks, where when wind is parallel to the laser beam, strong turbulence is present near the instrument sensing area. It is highlighted in white by the white line. Instead, when wind is perpendicular to it, most of the turbulence is contained below the sensing area, so do not impact measurements. It is also useful to evaluate some statistics around the gauge, so constructing a control volume just above the instrument sensing area, that is the part that is most probable to affect incoming hydrometers. It is possible to observe that both updraft and downdraft show a very non-linear dependence on wind direction. And so, considering the left image, we see maximum values of the updraft that can reach as high as 70% the free stream velocity, while for downdraft up to 40% the free stream velocity. However, mean values are about 10% of the free stream velocity. The continuous and the lines represent the Euron's results, while dots represent the results from the less simulation. And here we see that in terms of mean value, the two are quite close. However, some differences are present in terms of maximum values, especially in the case of the downdraft. On the right-hand side, instead, the percentage volume of updraft to downdraft is present, and so red represented the updraft condition, while blue represented the downdraft condition, and so in most of for most of wind direction, updraft is actually the prevalent factor in the field. However, in some condition, it could actually be overshadowed by downdraft that can be almost complete in the case of 157 degrees. So after simulation, of course, some validation is useful. And so here validation was obtained by placing both gauges inside the Dicka wind tunnel. And in the case of the ML calyx, measurements were taken considering both with and without the grid that was used to generate a different flow turbulence level. While in the case of the TIS laser precipitation monitor, the gauge was placed on a rotating board, and all 9 wind direction simulated were also measured in the wind tunnel. Cobra pressure probes were used to measure the flow velocity around the gauge, since they can measure flow quite close to the gauge surface. And so, starting from the EML calyx, we can see on the left-hand side some profile for the two turbulence conditions. So for low turbulence, both for low and high turbulence, upstream of the gauge, so the leftmost profile is actually very close to the numerical results, while some differences are present for the horizontal profile in both cases, especially very close to just after the gauge collector, where the maximum turbulence is present. And speaking of turbulence, also measure of turbulence taking the wind tunnel were also compared against simulated results, and show a very close. They are quite close. Okay. The same was also done for the TIS lateral precipitation monitor, and here we start with the Eurance simulation. So in this case, up to 65 points were measured for each wind direction and each wind speed that were validated. And here in the upper left corner, you see the grid of points that were measured for the gauge. And so starting from the wind direction of 0 degree, we see very good accordance, especially for the transversal profile, so the rightmost one, and it's still very close in the case of the profile just above the instrument sensing area. In the case of other wind direction, so 45, 90 degree, almost no difference is present between the probe measurement and the simulation results, showing a very good performance of the numerical model. Of course, since a very large number of points were measured, on those measurement quality was evaluated. So all the measurements that do not satisfy a minimal quality level were excluded. And after all the analysis, a total of 661 points that satisfy quality were used for a statistical validation. And of those, only about 60% of points presented a difference with the fluid dynamic simulation that exceeded the probe tolerance. So actually quite good results. In the table, I hope it's readable, a more in-depth analysis of each wind direction and wind speed. And so in most cases, very low mean error and standard deviation are visible. So value like 0.1 meter per second average error. However, for some wind direction, like for example 180 degree, very low quality measurement were obtained due to the high turbulence close to the gauge body and the limitation of the probe used. And so in this case, some amount of outlier are present. Solution scalability was also tested, running some simulation and some wind tunnel test at 2, 15, and 20 meters per second. And here, very good scalability is visible for 45 and 90 degree. Little worse scalability is present for a wind direction of 0 degree, however, it's still quite close. And also, larger simulation were compared, of course, against wind tunnel measurement. And here, left-hand side, quite good reproduction of the most turbulent part of the flow is visible, as expected by a larger simulation. However, for a wind direction of 0 degree and a profile above the instrument sensing area, actually lower accordance is visible in this particular case. However, on the other cases, very good accordance, like for example in the case of the wind direction of 90 degree, where almost no difference is present, are visible. And so, judging these results, we can say that less results are close to wind tunnel measurements in the recirculation zone, but are quite farther away in the separation layer, and we can see that. And also for a wind direction of 90 degree, both larger simulation with tunnel and Eurance results are very, very close. And so, to conclude, a much costlier larger simulation approach in this specific case do not provide a significant improvement for the analysis of the wind-induced bias for this kind of gauges. And so here a little bit of conclusion. And so Eurance simulation were run considering with the K-omega SST turbulence model and less with the well-adapted total eddies for two different gauges with complex geometry. A significant lower velocity was shown for the calyx, EML calyx, in the separation layer for the higher turbulence test. Instead, in the case of the TIS lateral precipitation monitor, significant dependence on wind direction is shown for the disturbance close to the gauge sensing area, with maximum disturbance for wind parallel to the laser beam and minimal for wind perpendicular to it. Both numerical models were validated using the velocity measurement, taking the Genoa tunnel, and both showed very good agreement. However, the much costless approach do not provide significant improvement. So there are some references that you can check if you're interested, and thank you very much.
All right, so can you see my screen and listen to me?
Yes, we can hear you perfectly. We can see your screen. Thank you.
All right. That's perfect. Okay, so hello everyone. I am Theodore Potsis. I am a PhD candidate in Concordia University under the supervision of Theodore. My presentation for today is entitled A New OpenFOAM Library for Modeling Wind-Induced Peak Pressures on Buildings. And I would like to basically start my presentation by giving you the outline of the evolution of computational wind engineering in the last decades for structural applications, at least from my perspective. First of all, we have in 1992, the formal birth of computational wind engineering from this seminal conference in Tokyo. And at that period of time, we had the first studies that captured mean pressures with RANS and LES modeling. Skipping to 1997, we can say that it's the first time that the importance of the turbulence characteristics of the incident flow were first highlighted. And at that period of time, we had the first endeavors to create synthetic inlet applications in order to express correctly these turbulent features. And we see also the transition from research from RANS to LES, since if we want to actually extract design values, we need time series, and this is something that we're able to retrieve with LES. Going forward to 2002, we have the first LES studies with synthetic inlets for fluctuating pressures on building envelopes. And at that period of time, we also see the transition of research to synthetic inlet. And we can maybe mention that for the next 2 decades, from 2002 until 2022, we have this research blooming, and we have basically 3 main approaches of how to properly define the inlet conditions to include the proper turbulence features to interact with the building. We can basically divide them in the recycling techniques, synthetic flow generator techniques, and the virtual wind tunnel approach. Now, I don't want to go into much detail about all of those. Something that I just want to highlight is that the virtual wind tunnel, it is the most computationally expensive. Synthetic methods are a bit complex to use, but all in all of those procedures are able to give us the correct inlet data if we want to really design a building, let's say. So in order to just to conclude all of that, in the last 3 decades, we've seen various applications, and we've seen that the target level of accuracy has been achieved from CFD to design buildings, but the codes still do not allow the use of CFD for design purposes. And mainly this is because it's very difficult to generalize these procedures, and it's very, very difficult to create a procedure easily applicable in the field. Now, in order to solve these problems and aid the current state of the art, we came up with a new modeling approach that we're trying to implement in the OpenFOAM area right now as a library, and this is called the dynamic terrain method. Now, the main idea of this procedure comes from the inspiration of the wind tunnel facilities. Here I have a picture of the wind tunnel at Concordia University. You see the feds, the building located at the center of the turntable. Now, basically, this building inside the wind tunnel, it interacts with this type of mean flow field, the very famous atmospheric boundary layer mean profile of the velocities. But if we really look at this profile, what happens at the instantaneous profiles, we see that at every instant of this experimental procedure, this instantaneous profile is a bit different from the mean flow. And as you can see, the more of them we compare, the more we see how much they deviate to what exposure we're considering. And when we consider, let's say, most of the ones we have in the experimental procedure, we see that those differences in the profiles basically create different exposures of the building. And the main assumption of this computational methodology is that we want to model each and every one of those exposures, each and every one of those terrains, and make them interact with the building so we can extract a pressure value for each and every one of them to generate the final pressure time series. To elaborate a bit more on that, here I have a computational domain that I've used. And if we introduce one of those instantaneous profiles, we see that close to the building, we have this generation of vortices. And a very, very important parameter is how we basically introduce this inlet data. And this refers, of course, to this averaging time window and the inlet frequency. So basically, we introduce this data as in a steady state, in a quasi-static state, in the inlet plane. And this flow interacts with the building and, of course, generates all of these vortices. And then, as you will see a bit later, we are able to extract the pressures we want from the building envelope. Let me go to the workflow now of the dynamic terrain. Let me go to the targets of the dynamic terrain first. So the first target is to define the proper average time window of the computational analysis. This is the inlet frequency of how we impose those profiles, these velocity profiles at the inlet. This, of course, refers to the capacity of the mesh to represent the small temporal and spatial scales, which is very, very important in order to represent the next target, represent the high frequency fluctuations that will interact with the building. And these fluctuations have an immediate impact at the peak values that will be developed on the building envelope. Another target is to gain control of the exposure conditions for its average time window, which is why we also, again, mentioned this method as dynamic terrain, since we want to be able to really control the exposure conditions for each and every one of those average time windows. And of course, we want to represent the target exposures for the entire averaging time of the analysis in terms of an open or suburban exposure of the building. And finally, something very, very important about this procedure is that it's based on coarse domain LES. Now, this is because we're targeting this application to be used for practical usage. And we know that there is a big difficulty right now to conduct CFD with very, very fine domains that we need. Just very briefly, a few words about LES. Basically, in this modeling technique, we have a division of scales to large and subgrid ones, and we treat them differently during the solution process. The large will directly solve them, while the subgrid ones will model them, and we have, of course, this filter to divide them that is related with the mesh size. Here I have the famous Navier-Stokes equations, of course, and how they create the LES equations. And now going into the workflow of a dynamic terrain methodology, first of all, we start from wind tunnel velocity experiments. We extract this time series for various heights of the atmospheric boundary layer, and we can create basically all of those instantaneous profiles that I presented a bit earlier. And what we do is we impose them in a quasi-static manner at the inlet plane, first of all, of an empty computational domain, in order to really make sure, first of all, that the velocity features and the turbulence is properly expressed in the domain. And this is done by using this time-varying mapped fixed value function of OpenFOAM. The first parameter we need to calibrate is the frequency of this inlet time series, this average time window. And as we were able to prove in a previous publication, the first thing to check is the accuracy of the spectrum at high frequencies. And as you can see in this figure, after the cutoff, the limit of the filter, basically of LES, the cutoff frequency of 0.96 here, we're able to really express correctly this energy level of fluctuations that are very vital to really have a meaningful interaction between the building and the wind flow. Now, the next step is to measure the turbulence decay of the incident profile, in the sense that when we introduce velocity data at the inlet, we know that they're going to dissipate as the flow travels downstream until it reaches the building. And of course, we need to make sure that the incident profile is the proper one that we want to use. Now, we have come up with a very simple scaling technique for that reason, in the sense that we modify the data at the inlet in order to change the incident profile. And as you can see here with this very simple procedure, again, I don't want to go into all the details, but I would be happy to talk about it after the presentation. We can basically scale this incident profile and make it closer to what we want to model according to the experiments. We do exactly the same thing for the RMS profile, for the standard deviation profile, in order to modify finally the turbulence intensity that will interact with the building. And as you can see, this is also done easily and successfully. And finally, we're ready to run the case with the building, of course, inside the computational domain and extract the pressure time series from virtual probes. Now I have this case here where basically what we do, we have the location of the pressure of the virtual probes, and we extract the pressures for each and every time step of the computational analysis. And the first thing we do is we do an averaging technique based on the average time window. So finally, we have a pressure time series based on this average time window. And then we impose a second average in order to extrapolate all of these values to a target output frequency based on the experiments we want to validate. So the final time series has this time of the experimental procedure that we want to validate. And of course, then we go and try to validate at least the mean, the standard deviation, and the peak pressure coefficients on building envelopes. Now, for the purposes of this presentation, I decided to present results for pressure coefficients on roof of a low-rise building. I use these two symmetry lines on the roof, S1 and S2, and I present here in the first column the mean values, then the standard deviation, and then the peak values, and comparisons between the NIST database, experimental results, and the dynamic terrain methodology. As you can see, we have a very good accuracy in those symmetry lines. Of course, it's very, very important to include non-perpendicular wind directions when we're talking about design conditions. And as you can see here, for the oblique wind direction of 45 degrees, for those two symmetry lines, again, we seem to be able to really model properly the mean pressure coefficients, and of course, more importantly, the fluctuating pressure coefficient that is used for design. I should mention here that this is a very coarse computational domain, around 3.5 million elements. And if we look at the state of the art, we see that in order to capture this accuracy of the pressures, more complex techniques are needed, and of course, a lot finer computational domains, especially for this perpendicular wind direction. Now, this is a work under development, of course, so I'm going to mention everything from now on as future targets. So the first very important thing for us is to generate this inlet data for the computational analysis based on the open database of Concordia wind tunnels. So we want to have a database available open so that people can extract this time series of the velocity from the experiments and be able to use them with the steps of the dynamic terrain method to see the pressures that are developed finally on building envelopes. For that reason, right now, it's almost done, but it's going to take a bit more time. We're creating this C++ library for public use. The target of this algorithm here is to, first of all, extract the wind tunnel data from the database of Concordia and create velocity time series at the inlet of the computational domain. It will give the user the ability to modify the inlet frequency, as we said, first of all, to capture the energy, the spectral content of these high frequency fluctuations, modify the mean and the standard deviation profile at the inlet in order to capture properly the exposure conditions for the entire analysis that we want, and modify this thing in 3 directions, which is something that I'm actually evolving right now. So we have the correct expression of this turbulence in all 3 directions of the flow field. And of course, this tool is going to be able to extrapolate all of this pressure time series to a selected output frequency based on the wind tunnel results that we want to validate. Something that I'm targeting also, which is a bit of a difficult procedure, is to make this tool as user-friendly as possible, since it's a bit difficult when implementing things in OpenFOAM to make them user-friendly. And we want to include more practitioners in this conversation and in this tool. Okay, so finally, I think I'm a bit earlier on time, but I think I can conclude here. Right now, we're developing a new OpenFOAM library for modeling wind flows and loads in the atmospheric boundary layer. As we were able to prove, we are accurately representing, first of all, the spectral content at the high frequency fluctuations at the incident flow, which is a novel accomplishment with LES based on those assumptions. We're able to represent accurately the mean and the turbulence intensity profiles at the incident flow that interacts with the building, the mean, standard deviation, and peak values on pressures of a low-rise building. And I should also mention that these applications have been expanded to wall loads and higher buildings than just low-rise ones. And the conclusions are still the same. We have very good comparison with the target experimental results. And finally, for me, the most important comment to highlight is that this procedure, from our perspective, is a simple one. It's a procedure that does not use the complexity of synthetic inlet, first of all, which is one very important point. And second of all, it's based on coarse large-scale simulations. And this gives the ability actually for practitioners to start using it as a tool. And we're starting the conversation of how basically computational wind engineering can finally be introduced in a very specific way in code provisions and be able to be used for calculating peak pressures on building envelopes. So these are the references I use for the presentation. Thank you all very, very much. And of course, I'm here for any comments or questions you might have.